Hello, I'm Ashley Ford Versipt and excited to present in this survey session on chemical reaction engineering. I'm honored by the invitation from the Education Division. So my presentation is about active learning exercises for teaching reactor design. A brief introduction about myself and why I was asked to do this. I have taught chemical reaction engineering for chemical engineering juniors at Oklahoma State University for the last 6 years, annually each spring. I also co-led the AICG Education Division's virtual community of practice that was on chemical reaction engineering and process control during spring 2020. I currently serve as the chair of the American Society for Engineering Education Chemical Engineering Division, and I've also published and presented on this class and others several times in the last few years. The learning objectives for this talk are for you to be able to see examples of active learning exercises for chemical reaction engineering, and for you to actually be able to take these tools and put them into your own classes or reuse them in other ways. And so all of the in-class problem files are actually in the iPosters platform associated with this presentation. They're in a Dropbox folder, and I have specifically titled some to correspond to the names here, but I've also provided the entire Word document set and the solution set for all of the in-class problems that I use in this class. I also am going to share a few memorable analogies that perhaps you can adapt into your own courses or inspire you to think about creative and fun analogies for using in your contexts. So on the first day of my class, I show this image overhead. And it's supposed to be eye-catching, different, unexpected, and because it's very unexpected, I hope it will be memorable. This visual is very compelling. It involves two witches brewing a potion, and there are spell books or recipe books behind them. There are various ingredients. We have a heat source. We have different phases of matter. We have no safety equipment to speak of. And this becomes a conversation starter for my students. This is from the front cover of Octave Levenspil's Chemical Reactor Omnibook. So those of you familiar with his work may have recognized this image. And a more recent edition of the book has this small dragon, which my photo that I show the students does not involve that dragon. But we use this as the first in-class problem. Very first day of class, we call it the witch's brew. And so the purpose is for students to generate the list of course topics. So rather than me rattling off a bullet point list of all the topics we're going to cover when they don't necessarily know why or even know the terminology yet, I want them to explain and generate a list of ideas that they think are important for this course based on that image, and then that becomes the basis for being able to explain the course topics. So I have them describe what's happening in this photo of the two witches. I asked them to list the different types of physical and chemical properties of the ingredients that they see there. I asked them about the phases of matter, so just touching back to some of their general chemistry type of background. I asked them what engineering processes that they learned about last semester that may be happening here. So my course falls in the second semester of their junior year, and previous to that, they have just finished chemical engineering, thermodynamics, transport, and fluid mechanics and heat transfer. And so I want them to be thinking about connecting this content, building upon the previous courses. The next question is, what do you think would you need to know about the process in order to take the magic out of the process and incorporate scientific analysis and engineering design principles? What would the witches need to consider to scale this process to create thousands of potions to sell to customers? And finally, what aspects should receive particular attention for safety of the process? So we start thinking about safety, we start thinking about design, and we start thinking about what are kind of the key formulas and variables that we need to start to consider in order, and processes in order to be safely manufacturing large scale quantities of reaction products. So sample solution here, I purposely have truncated some things, but I just numbered a few of the questions, and then these are the things that I would write on my Surface or on an overhead projector and show to the students. So they often think of the heat transfer fluids. They took PChem also usually this semester directly preceding this course, thermo. They think about reaction rates, energy requirements, which reactions occur as being important to know about, the temperature, the pressure, concentrations of raw materials, being able to track the progress of the products and intermediates by concentration, and knowing what the reactants and products are. We talk about, they look at it and they think about for the scale up, do they need to have many of these batches happening in parallel, or do they need to move towards a continuous flow type of operation? They have mentioned the amount of fuel required, the efficiency of heating and mixing. Safety is a big one that they do bring up, the timing, and then we also briefly discuss some mixing and control issues with scale up. And then for the personal protective equipment, they note that it's an open vessel. There are vapors, bubbles that could overflow. There's also an open flame, so that may not be the best heating source. They also mention flammability, explosion. But this, I get students working in small teams and they brainstorm and they're talking to each other on day one with this very memorable witch's brew. I also infuse this photo or this illustration throughout the course. When we switch to a new chapter, I will ask them to think back to that sketch and think about which part are we now addressing. So when we do stoichiometry, we reference the spell books with those recipes. When we talk about heat transfer, we look at the flame. When we're talking about the vessel choice, we look at the actual cauldron there. And I actually show them a series of Google images of cauldrons and a series of Google images related to pressure cookers or crock pots, and have them think about for different applications, you might choose different of these cauldrons or different crock pots or different pressure vessels, depending on the size of how many people you need to feed or the size of your household and the meal that you want to cook. And so that is a piece, that illustration comes up over and over again throughout this course. I use it to connect to the course map. And so some of you may be familiar with Linda Nelson's book about course maps or others that are out there. But basically, I have mapped the individual topics of the class to align with Scott Fogler's chemical reaction engineering algorithm that he uses in his books. And so in the there are 6 steps in this algorithm, but in the course, we're going to talk about different types of reactors, and there's simple cases and complex cases. We can have number of reactions to be one or multiple. When we're on the rate law, the things that are going to affect the rate law is how many reactions do we have, what phases do we have, and what type of information do we have. For the stoichiometry step, it's going to be which chemical reactions, which phases. The combine and evaluate, we're going to think about whether this is analytically or some type of numerical technique. And for the energy balance, we're going to think about if this is isothermal or non-isothermal scenarios. And so I also show them this at the beginning of every class period and show where is our content on this course map. So again, rather than just saying, here's all of the topics, which are certainly in our course learning objectives, but I have this course map so that they know where we are and how what we're covering right now applies to changes in the mass balances or mole balances or changes in the stoichiometry step, etc. So a key part of the in-class problems and the active learning that I do is this gradual release of responsibility. And some of the staff in our Institute for Teaching and Learning Excellence introduced me to the pedagogical concept of I do, we do, and then you do. They saw what I was doing and they gave me this formalism and I thought it was perfect. So the idea is that you start with modeling the instruction. Maybe you're working an example problem or you're telling some theory. Then you share the instruction. So that may be asking students to follow along as you're doing an example. That may be the level that you can get to if you're doing a video type of instruction. The guided practice, you're usually involving the students doing it, either you watching them or the students doing it in teams, and you're watching those teams, interacting with those teams, guiding them, providing feedback as they go. This could work online in breakout rooms, but in person, it works well to kind of rotate around the room or to have some teaching assistants helping you with that. And then the independent practice is usually them doing it at home or in small groups on homework assignments or on exams. So all of the in-class problems in my class reflect this type of giving them the opportunity to for them to do it while I'm in the room or while I'm on the Zoom call so that they can get some immediate feedback and collaborate and have some guidance, but they can practice with the concept before they're responsible for it in a homework or an exam setting. One of my favorite in-class problems, when it becomes this day of this lecture, I celebrate grilled cheese day, and I always tell them, I'm sorry I didn't bring you any grilled cheese. The class is typically at 8:30 in the morning too, so I don't provide them food. But this is a real-life stoichiometric table analysis, and so I want them to think about, materials that they have worked with rather than chemical A and chemical B. This is very tangible. And I actually had my sister, who was an English major, and my husband, who studied education, to think about working through this. And so they can actually fill out the entire chart, not in the chemical engineering terminology, mathematical terms, but they could calculate all of the numbers for these questions with their backgrounds. And so it's should be intuitive to think about how many sandwiches can you make based on the raw ingredients that are provided. But the most commonly asked question I get is, can I have a half of a sandwich? And indeed, you can have half of a sandwich. It's shown here. And at Panera and other restaurants, you can order a half a sandwich. Even Subway has 6-inch sandwiches. And so they have to think about kind of the practical implications. But when you have something like a mole of something, you don't just have to have quantized amounts, single moles. You could have integer, or not just integer, but you can have real values. And so this one, they walk through the exercise of making these grilled cheese sandwiches, but they're putting it into the stoichiometric tables in the format used for homework and exams. This particular in-class problem involves reactor configurations. And so this is an illustration from Fogler's Chemical Reaction Engineering textbook. And there's a really nice example in the book on the page that faces this illustration, but students don't necessarily immediately see how they can generalize this. So the idea is thinking about when you have the context of multiple reactions and you need to choose a reactor to maximize selectivity for that specific set of reactions, you might have you want to maybe have relationships where concentration of A can remain high while the concentration of B can be low, or flip those around, or maybe you need to be able to remove product, or maybe you need for the product concentration to be able to be high for some reason, or the temperature being high or low in order to have a certain reaction be favorable over others. And so this is a set of illustrations of all of the main reactor types that we consider in the whole course. And what we do for the in-class problem is think about, for each of these cases, what will be high and low? Will both A and B be able to be relatively high, or can you make them differentially high and low compared to each other? So for example, the semi-batch reactor, if everything in there is B to start out with, then you have a high concentration of B, and you can in a controlled manner, add A so that you can keep the concentration of A to be low. So that's the kind of thing that we think about. And so that process, though, the students don't always grasp that immediately of how to think about which ones are high and low. And so I asked them as an in-class problem to work through that. And then I asked teams to speak up, since there are so many of these pairs of students. And so the ones that are less confident maybe know that they know maybe the first one. And so they'll jump in on the ones that they're more confident for. Or if I have talked to them and given their team some guidance in the in-class problem time, then they will generally speak up, or I may call on that team. But I encourage them to take our results for this and write it in their textbook next to those illustrations, so that when they can think about it on their homework assignment, but they can also have that as a handy reference when we go to do it on an exam, instead of having to reprocess and think through all of that every time. But if they process it together once, then we can have this as a handy reference. We also do a number of videos in the class and reflect on them. So when we start the middle of the catalysis section, or the kinetics section, the middle of the course, we are I have a few memorable videos that I show them. So the first one is called Reaction Kinetics in Blue, and on the same day I do Reaction Kinetics in Blue and the next video, and I ask them to reflect on it. In this video, I show segments of it, but it's talking about two reactions that happen competitively. And in the video, the instructor asks these participants to hold up blue paper plates. And part of the reaction is in the gas phase. So they show the white side of the plate above their heads if they're in the gas phase. Shake up a flask, the gas becomes then dissolved in this liquid. And the competing reaction is to turn blue when these molecules are together. And then as they dissolve, they compete, turns back clear, and then the gas goes back into the vapor phase. And so the plates, if they're reacting and turning blue, the two people that collide with each other turn their two plates to the blue side to face each other. When they go back into the gas phase, one of them goes back up. And so it's a really visually compelling illustration of this particular reaction, but he also shows it, the actual experiments of the flasks in real time with a color change that is concentration dependent and temperature dependent. So it's a very excellently done video from Flint Scientific. And all of the links are in this presentation. And so in the iPosters format, in the PDF of this presentation, there's a comment that includes all of the links, but you can also directly click on the videos and you should be able to get to the YouTube links. I also have provided a shared folder where this in-class problem is called kinetics videos. The next one is a video from Crash Course from their chemistry series, and they make the analogy to kinetics as chemistry's demolition derby. And so it's a really fast-paced, fun, instructive video, but about the kinetics and the crash and the collision of having to hit at the right angle with the right force in order for there to actually be a fruitful chemical reaction. That if things very slowly interact, there may not be enough kinetic energy to actually have the reaction, or if they hit in the wrong spot, they don't actually hit at the receptors, they don't hit with the right molecules touching, then you won't have the right type of collision. So it's a fantastic analogy, and actually throughout the class and in my research, I refer to these collisions very visually, reflecting back on this video. The other video that we actually watched twice in the course is the T2 laboratory explosion video from the Chemical Safety Board. This is a very well done video, as are all of the videos from the Chemical Safety Board. This particular one describes a runaway reaction that leads to an explosion at T2 laboratories. We watch it on the first day of the class when the students don't know any of the terminology yet, but they can recognize the importance of chemical reaction engineering and the gravity of the safety concerns that they, as chemical engineers, need to keep in mind as they work on reactive hazards. So it sets the tone for the class as being interesting, but also really important. And so we talk about on the first day, what do you think? What are your observations? On the last day of the course, after they've actually read in detail about this case study in Fogler's book in the unsteady state reactions chapter, unsteady state heat transfer, they think about what are the things that you've learned in this course that now make you understand this scenario better, and what are the what did they do wrong here? And students see this, and they may also see it another time in design. So one of our senior design cohorts for the senior spoof video actually took the music that's the background of this and used it in their senior roast videos, the transition music. So it's a very recognizable theme if you've heard this multiple times a semester for multiple years. So anyway, I have fond memories of this video. Very instructive, very useful. Additionally, here we go. The most memorable analogy that I make in this class relates to catalysis and the movie Armageddon. So in Fogler's book, there is a wonderful diagram of the mass transfer steps and the surface reaction involved in heterogeneous catalysis. So external and internal diffusion, adsorption, surface reaction, desorption, internal and external diffusion to get materials back into the bulk. And I was looking at this diagram and thought, this is the plot of the movie Armageddon. Now, our students are a lot younger than I am, and this movie came out in the summer of 1996, and some of the students were not alive yet. But I show this trailer without introduction at the beginning of the course period, and they say, what is going on? But they see it's a very compelling, interesting movie. This was a blockbuster hit. And they have to travel through space and land on the surface of an asteroid. They are drilling engineers. They have to drill into the core of this asteroid where they place a nuclear bomb. They have to detonate the bomb. And then the challenging part is getting off of the surface and getting out of there before the nuclear bomb reacts. And so I make this analogy. It's quite memorable. It's also humorous for the class because several of them then follow up with me and say, "Oh, I just watched this movie," or "It's one of my favorites," or "It became my new favorite." And so it's a fun conversation piece as well. So these are the main pieces I wanted to communicate to you. I want to just briefly, in conclusion, talk about some ideas for translating these active learning ideas into the virtual learning format. So highly recommend having a Google Doc or some sort of collaborative online document that you can give students a prompt with questions and then they can answer individually or anonymously. They may be less likely to vocalize through their microphones depending on the size of your class, but they may be more likely to interact there. Also breakout rooms, just knowing that it takes longer in those than before for just pairing up and working in small groups in class, and they're less supervised because you can't overhear conversations unless you're in a specific breakout room with the students. In my course this semester, I'm actually taking some of the out of class videos and having them reflect on them in advance. And I give them a small, very small um, uh, grade for having reflecting on those. And so that could be also a way to do this. I find that with the online learning, more of the we do stage, I'm doing a lot more examples versus having them do it together with each other with me interacting. In my hybrid course, it's not really feasible for the students to both talk out loud and hear their peers and me to do the video recording all at the same time. So I'm doing a lot more of guided examples with encouraging them to interrupt me and ask questions, but I'm also recording those so then they can go back and refer to my step-by-step instructions when they're ready. You can also give guided homework feedback through virtual office hours. If it's tricky to supervise the in-class partnered problems, you could also give guided instruction of the homework solution as a way that's more of a, you've tried it, here's now how that solution worked. And then for course projects, these still scale well to having virtual learning environments. And so I'd encourage you to see my other presentation in this meeting titled Choose Your Own Kinetics Adventure, Student Design Case Studies for Chemical Reactor Design Projects, that talks about the projects I use for active learning in this course. So as a dissemination, all of the in-class problem files are located in the iPosters in a Dropbox folder. There's the fun examples that I've shown, but then also all of the calculation-based we do and you do problems are there with a Word document, a PDF document, and then the solution PDF. I also have all the links embedded to the videos. You can directly contact me for further details. Easiest way to reach me is through email. So thank you very much, and I welcome your interaction, and I hope that you can take some of these ideas and incorporate them into your own courses. Reactor engineering has been one of my favorite courses to teach, and I really am passionate and interested in this course, and so happy to brainstorm or share any other files, exam files, other materials with any instructors. So please feel free to reach out to me. Thank you very much.